So today we will discuss about OFDM, orthogonal frequency division multiplexing. So OFDM is the basis of all 4G wireless communication, that is known as wideband OFDM. It is also the basis of WiMAX. It is the basis of digital audio broadcasting, digital video broadcasting. It is also the basis of asynchronous digital subscriber line, wireless local area network, digital video broadcasting terrestrial in Japan and Europe. So the main idea behind the OFDM is, first, it is based on the MCM, that is multi-carrier communication. In multi-carrier communication, the channel is divided into number of subcarriers, like n subcarriers. So there are n subcarriers and we have n data streams. So the n data streams are put on the n subcarriers. The most important thing is that these subcarriers are orthogonal. So with the help of orthogonality, we can make the arrangement, the overlapping of the subcarriers. So there is a ultimate result is that there is saving in the bandwidth. And lastly, the multiple carriers are combined through IFT. So before multi-carrier communication, there was a single carrier communication. In single carrier communication, only one carrier was used for the entire communication ports. So waveform duration is, suppose, let its duration is t. So the symbol time will be t is equal to 1 upon b. B is the bandwidth. The symbol rate will be 1 upon t, that is b. B is the bandwidth of the system. So we can say that in single carrier communication system, if we have a bandwidth of 100 megahertz, so its symbol rate will be 100 Mbps. 100 megahertz, not 100 Mbps. The figure shows the whole bandwidth b is carried by the for transmission. So the expression is s of t is equal to x of t, where t is kt, k plus 1t. So in single carrier communication system, we transmit each symbol for t seconds. In every t seconds, we transmit each symbol. So x0 symbol is transmitted in t seconds. In another t seconds, we transmit the symbol x1 and so on. The figure shows that there are multi-carriers, number of carriers are there. This is a single carrier and this is the OFDM. So you can see the difference between all these things. In OFDM, we can see there are in multiple carriers, but they are overlapping to each other. So the result is that we can save more bandwidth. So in single carrier communication, we are transmitting one symbol in every t seconds. In multi-carrier communications, what we do, the whole bandwidth is divided into number of n subcarriers, and each subcarrier actually has a smaller band, and this band is called a subband. Because we can say that the whole bandwidth is b, it is divided into n subcarriers. So the bandwidth of each subcarrier is equal to v upon n. This is also the subcarrier spacing, and it is also called the bandwidth of subcarrier. Suppose consider a bandwidth 256 kHz, and if 256 kHz bandwidth is divided into 64 subcarriers, so the bandwidth of per subcarrier will be 256 divided by 64, that is 4 kHz. So each subband is very narrow. What we did, we divided the whole subcarrier into number of subcarriers. In single carrier communication, we were transmitting the information over one carrier. In multi-carrier communication, we are transmitting the multiple information to multiple carriers simultaneously. Okay. So this is the scheme, multi-carrier transmission scheme, where the subcarrier frequency is given by Fi is equal to Ip upon n. V is the whole bandwidth, n is the number of subcarriers, where I, the value of I is from minus n by 2 minus 1 to n. Single carrier communication has one carrier and one data stream. Now n subcarriers and n data streams. So in multi-carrier communication system, we are transmitting multiple information on n subcarriers. So we can say the modulated signal stream xi, that is ith symbol, ith set of symbol, e raised power j 2 pi fit, that is ith subcarrier, where the fi is the center frequency of the ith subcarrier. So xi is the ith symbol, and this one is the ith subcarrier. So we transmit first symbol on the first subcarrier, second symbol on the second subcarrier, and so on. So we can say there is a composite transmitted signal will be s of t is equal to number of subcarriers, summation of number of subcarriers Si of t. So xi of t is equal to xi e raised to power j 2 pi fit. There from here si of t is equal to xi e raised to power j 2 pi fit. Okay. So this is the composite signal. We can replace the fi by b by n as we saw previously. Fi is equal to I b by n. Okay. So now this is the composite signal that are transmitted. So when this is transmitted and it is received at the receiver, so some detection scheme is there to detect the signal. Right now we are considering there is no noise, so the received signal will be the whatever the transmitted signal. So the received signal S of t is equal to summation of xi e raised to power j 2 pi fit. Actually the detection scheme is based on the coherent demodulation. So what we do to decode the ith subcarrier, we do the correlation with between the composite signal with the ith subcarrier. Suppose we want to extract the information, first information, that what we'll do, will correlate the composite signal with the first subcarrier. So all the informations are extracted by correlating all the subcarriers. So what is the principle behind it? It is the detection, that is the b by n, this is the scaling factor, integration from 0 to n by, that is the integral over one period, y of t e raised to power j 2 pi ft. Here we are doing here, we want to extract the information that is on the LH subcarriers. So this is like a matched filter detection. We can say this is a matched filter detection operation. So it gives the output. So all the subcarriers which are not equal to L will give the result 0, and whatever the information on L subcarrier it will give. So the output will be n by b, that is the output for I is equal to L. So after demodulation, ith subcarrier b by n x by L plus n by which that is xl. So we get the lth data that was transmitted on the L subcarrier. So for every data we have to perform matched correlation, matched filter detection with all subcarriers. This is the schematic diagram of multi-carrier communication transmitter. First, the information is converted to parallel form. So number of number of modulators are there. After modulation, we again convert from parallel to single stream. This is the composite signal that is transmitted. At the intersection, what we do? Composite signal is received. It is convert first into parallel form. So the opposite operation of the modulator, that is demodulator, is performed. It is also called the correlation. After correlating, we convert the parallel signal to single. This is what the operation at the MCM, transmitter and receiver. But what's the problem in the MCM? What we are doing? We are doing nth symbol with the nth subcarrier. So what we gain in the MCM? We are using n symbols using n subcarrier, the n by b times. So in the SCM we were transmitting one information symbol into 1 by t times. Here we are also transmitting the one symbol 1 by t times. The result is there is no gain in the MCM. Okay. Suppose we consider we have the bandwidth of 1024 kilohertz, it is 1.02 megahertz. There is a coherence bandwidth, like it is like a 200 to 300 kilohertz. If we consider single carrier communication, here bandwidth, that is the 1024 kilohertz, is very greater than this, is 200 to 300 kilohertz. So what happens in the single carrier communication? In the frequency domain, there is the channel becomes frequency selective, or we can say in the time domain there is a intersymbol interference. Here what happens in case of ISI, the symbol interfere with each other. So the received signal is very highly distorted and it's very difficult to extract the information for the receiver. While for the multi-carrier communication, where we have divided the whole bandwidth into number of subcarriers, and each subcarrier have very less bandwidth. Now each subcarrier is having the frequency that is very less than BC. So now each subcarrier experience flat padding channel in frequency domain, or we can say in the time domain there is no ISI. Now the symbol will not interfere each other. So the reliable detection scheme can be applied for the narrow band subcarriers. Okay. So but what's the problem? Problem in the MCM is that we need number of modulators at the transmitter, number of demodulator at the receivers. When the number of subcarriers becomes to be large, so we require that number of modulator at the transmitting end and that number of demodulator at the receiving end. One more problem is that the receiver must be matched with the transmitter in phase. So we can say overall more amount of hardware is required. To solve this problem, Weinstein and Abbott in 1917 gave one solution that is called data transmission via frequency division multiplexing using DFT. So what is the meaning of? We will transmit the data using frequency division multiplexing, but not through the modulators. But we will not use the modulators. We will perform the action of modulation and demodulation through DFT and IDFT. So this is a very efficient way of generate these samples is to IFT. So we now require no modulators and no demodulation. This is called the OFDM. So we can say the OFDM is based on the multi-carrier communication. This is the schematic diagram of OFDM transmitter. First we will convert the serial signal into parallel signal. IFT will be performed. After IFT, the parallel signal will be converted into serial signal. Now the composite signal that will be aired in the for transmission. At the receiver side, what we will get the information. This in form of serial converted into first parallel form. The reverse operation of IFT, that is FFT, is performed. Symbols will be detected for each carrier. Now parallel stream will convert into single stream. So here the one more problem is that is the ISI, inter-symbol end-to-end. This problem arises due to multipath. What the multipath? Multipath cause delay spread due to ISI. Multipath cause delay spread produces ISI. ISI is produced by the multipath cause delay. So what we do? We insert some cyclic prefix. So the next modification in the OFDM is the cyclic prefix. Okay.